All right. This title is not a frivolous. So I'm going to suggest to you that we don't have formalisms for talking about classes, and we therefore do not understand very well what classes are. So this is sort of related things. So the first part of the talk will be about the sort of formalisms that we have and why they are inadequate for dealing with classes and therefore classification. And the 2/3 of the talk will be about this new formalism that we have been working for many, many years. And this is just hot off the press, even though this is the 5th version, but it's a much more satisfactory version. So let's take a look. We have to deal with very basic issues here. First, what is a numeric representation? Well, this mapping did not really appear for a long time historically, but eventually we began to represent objects by numbers. Primitive tribes are still using knots and so on, so the numbers actually should be thought of in this way, not really as representations of things. They began eventually be used as representations. But in any case, this is sort of a view of what is a numeric representation is. Notice there's no concept of class here appears. So numbers, you know, we have natural numbers. There are no classes there. And natural numbers is no different. In fact, even if you go to real numbers, so this step is not a big step as far as the representational formalism is concerned. What I would like to allow, I want to allow questions during the, not discussions, because then we can proceed at a reasonable pace. Discussions we can do at the end of the talk. So first of all, a little bit about the classes. Well, if you look carefully sort of at objects in the universe, it turns out there's no single object that exists outside the environment of its class. So these are tightly linked things. Whatever we look at, there are always associated classes. There's no object that exists outside the class. Sort of, they are coexistent concepts. So it's important to understand then that there must be some tight link between objects and classes. And that's sort of the business of induction. Is the reason biological information processing is so effective, it sort of relies, it's a built-in mechanism. And therefore, it must exist in nature, too. So it's not our invention. It must exist. Let me propose the definition of what means class-oriented representational formalism. We want to have a formalism that does the mapping of objects, but that this mapping automatically induces the mapping of the classes. So the way we define classes in the representational formalism should correspond to those classes. So we should not invent then what the definition of class is. It must come with a representational formalism. So those two postulates. And I'm going to discuss them in greater detail in the next slides. So what are the implications? I'm saying non-trivial, but it's not a particularly difficult one. We can discuss later. That first of all, that the class must be induced by object mapping. So it's not something we should be swearing a lot about introducing classes. And they should automatically capture the classes in reality. So here is our representation formalism. Once I define class here, it should capture exactly the corresponding class that exists in reality. And we will discuss later on why conventional representation, certainly vector space representation, do not satisfy this property. And also, what about the general structure of this concept? So we're not going yet into details, but it's something about general formal structure, what we want to have. We would like to have this situation that class representation must be expressed via basic object operations. If we violate this, we would violate the first basic axiom. Now, I'm just drawing your attention in this slide that we don't have the concept of class representation, and this is not really an accident. Even though it's quite an unreasonable situation to do classification without the concept of class representation, but I'm saying that it's not accidental. It just happens so that conventional formalism do not really support an adequate concept of class, so we kind of have to add it post hoc. So you can think about that situation, to which extent we have the concept of class representation. Now, moving on to this sort of structure, or what we want to have. We want it to be sort of inductive generative structure. So what does it mean? You know, generative structure is similar to what Chomsky was talking about grammars. We want to be able to generate every object in a class, and only those objects. And it must be inductive. Now, inductive formal grammars don't possess that property. Inductive, it means it must be effectively and reliably recoverable from a small training set. That's what inductive is. So this is just, I'm reminding, there was syntactic popular area in 70s, 80s, syntactic pattern recognition, where they try to adopt formal grammars to describing classes of parents. But it sort of fizzled out because of the problems I will discuss in a moment. So what is it related to, the inadequacy of formal grammars? Well, Chomsky actually never believed, as I mentioned here, he never believed in induction because, first of all, on the one hand, he couldn't see connection between formal grammars and induction because there is no tight link between a set of strings and the formal grammars. Sort of formal grammars is sort of kind of God-given, right? Somehow it appears with all the rules and productions and so on. And the difficulty, of course, has to do with even the underlying string representation. They just don't carry enough information to allow this recovery of class representation. Well, here's just a simple example. If you take two strings, because they don't have formative history embedded in them as a part of the representation, you can't really distinguish between those two strings, even though if you go to a little bit more precise representation, this is not tree, this captures the formative history, you will see that they're different. And this is what is indicated with green and red, that you had ABA and then ACA applied, where the second A was the context. While in the second case, the first A was the context, which is very different situation. Okay, I'm going to discuss a little bit vector spaces several minutes. Well, here's a formal definition just to remind you what a vector space is, you know, this famous 8 axioms. But basically, you have two operations. Now, what does that mean from applied point of view, where you define vector space in this way? This is a sort of standard formal definition of this as a structure. Well, so we must assume that representational structure is the algebraic structure. There's simply no other candidate for representational structure. So we must assume that it is these operations that act on objects. And accordingly, here I'm just discussing why this was systematically overlooked at. But accordingly, what are we allowed then if we assume that these are the operations on the data, and that's what mathematical description of that formal structure is, we must demand that the class representation is expressible via these operations. The only candidates then become affine subspaces, just shifted these linear subspaces, because they have to be consistent with underlying structure. Now, from applied point of view, this linear generativity is obviously is going to capture.
So why can't you represent a class as a half space, for example?
Repeat the question, please.
I'm sorry. Why can't you represent a class as a half space if you choose a vector space for representing items?
They do not sort of fit this standard mass. You want to have it. You want to have class representation. Every element in the class be generative. In other words, the class description must be of generative type. Every element must be expressible via basic operations of class representation. So you would not be, if I give you a training set, and also here is inductive, the second part comes in. You want it to be recoverable uniquely from a finite training set. So how would you recover? So you want to have these both things, generativity and this. How would you define then? How would, if I give you a finite training set, and you would say that class would be half space, which half space would you choose?
Maybe the maximum margin half space. Let's say the half space that separates the training data.
No, suppose I give you just one class. This training set from that class. How would you choose which class representation would be reasonable for if I give you whatever, 20 vectors?
Of one class.
Yeah.
So
How would you define? Because you want to have those two properties, the generativity, and everything should be expressible via basic operation, this vector addition and multiplication. How would you define class elements? How would you give me exact, you have to generate every class element.
why do you feel that the stability is necessary for a...
Well, because if you think about, here is the real classes, and here is your formalism, we want to have the mapping, the object mapping induces class mapping. So if I have certain objects in the class, I want to be able to generate every object of this class only and only this object in the class using class representation. I want to have this one sort of one-to-one mapping between real objects and objects in my formalism.
So one thing that's been proposed for one class classification is to find the half space whose coefficient vector has the smallest 2 norm or something that satisfies constraints that enforce the fact that all members of your class are on one side of the half space, for example.
But again, if you take, again, let's go back to the real object in this mapping. You remember this mapping from real object into your formalism. You want to assure that after you do this, that all objects that you can generate in your formalism, every object that you can generate in your formalism, correspond to the physical object that you're dealing with the class you're dealing with. I mean, this mapping is very important because you're mapping the actual object into objects in your formalism. So you want to have a very tight link between the actual objects and the object that you have in your formalism. So once you say it's a class representation, you have to then claim that every object that falls within this class has a corresponding object in reality, which will not be the case. You want to have, it's a strong restriction. It's a very strong restriction on what you want to have as a representation of formalism.
Yeah. So I guess depending on what you call a class, which I guess is what we were talking about over lunch, there would
well,
be
no, you don't want to call anything artificial class. You want to define class in such a way that this mapping is validated. That once you, because representational formalism is something that you're going to use to represent the actual objects in whether it's a web page, it doesn't matter. You're going to use that representational formalism to map objects. So once you are in your representational formalism, now you have to live here, but that means you cannot invent the concept of class that is not meaningful over here. So once you map the object, you are done. You are not allowed, you don't have any other means to change what the class of actual objects over here on the left-hand side. Because you're dealing with real objects, you're just representing them in this formalism on the right-hand side. So once you map them, that's it. You have no control. So the whole point is that once you do this mapping realize, you want it to be automatically induce the mapping of this class onto this class. It's a strong requirement, but what I'm suggesting that this is sort of a necessary requirement. Because then, you see, if you do not satisfy that condition, you will be defining classes here that has no reality over here. And that's a problem.
It seems to me that it's impossible to define a
Well,
formalism.
you will see now. That's what I'm going to talking about. This is most of the talk.
But then the question might be: are there things that we would, you know, are there things that we would call classes that are not captured by this formalism?
No, but
if you define a class to be things that are captured by this formalism, then
but you will see. No, you will see if the formalism is universally applicable. Because this formalism, all object can be encoded. Therefore, it's very easy to check if there are real classes that once you have that mapping and you use this formalism, then if you can find classes here that are not classes in your formalism, then you're done. Then you know it's not good. But it is. You will see it is not like that. So anyway, what I'm suggesting that to compensate for the above paucity of not classes, but these classes according to that definition, and in violation of sort of wisdom in mathematics, one brings alien class representations, and therefore alien classes. Like you use various, so you bring things like nonlinear functions and other things to define classes. They have nothing to do with the structure of this vector space, which is algebraic. This is a representational structure. That's the whole point. That if you want to treat objects this way, if you want to take your representational formalism seriously, you must take the operations on objects also seriously. So here's just, this is a typical picture, okay? Here is your class, and you have some nonlinear decision surfaces here. Now, everybody got used to this. So it took me 10 years to ask this kind of question because I also was used to these things, assuming that that's okay, you know, this is how things look like. But the question is how meaningful and informative such class descriptions, if we call these classes. What do we learn when I draw these curves in the vector space? How much did I learn about anything real? I mean, because these classes correspond to reality. How much am I learning about reality when I'm drawing these kind of curves in a vector space of surfaces? What am I learning? Well, it's useful to ask this question because you want to be able to say that when you got in class representation, that you learn a lot of things about reality. Because that's sort of the purpose of induction, and this is where the hidden induction, this is what sort of philosophers thought, that we should be able, you know, when we say we learn something, class, we should get wiser. I mean, what are we learning about actual objects when we draw this? But anyway, let me move on. So there is no tight link between a training set and a class representation, and that's a big problem because we want to have a much tighter link, so it's things are uniquely sort of deducible, the class representation. And then, you know, so what are we learning during the learning process, basically? So the problem is not with learning algorithms. That's what I'm saying. It has nothing to do with learning. It's a much deeper underlying problem with the representational formalism itself, because the structure of this representational formalism is such that you cannot you cannot remedy this deficiency to begin once you're there. So I'm saying the modern trends in machine learning is, again, these distances, kernels, and so on. They don't change. I'm just listing again. It doesn't change the basic situation that we have been discussing. You still don't have meaningful class representation, and that's a big problem. So we've got to move, as hard as it appears, we've got to move on. And the benefits are tremendous, because once you have that kind of formalism, you are really doing sort of, it's not just important for information processing, classifying web pages, but you also, from point of view biological, I mean, when you're doing, when you have these protein data banks, you know, you have a good description of these classes too, meaningful description, which would be then very illuminating to biologists. It won't be just something that one uses only for some strange auxiliary purposes. And of course, as far as the search engines are concerned, well, imagine if you have that formalism, you can, so you represent classes, and as a basis, you use it as a basis for organizing search engine, and then the query will be either a class element or description of a class. Two things are possible. So the user via certain interface either will specify class element or will specify description of class, and he will get, as a result of query, the class itself. Well, here I'm discussing, where the origins of this work go back to 1990. It's a long paper published in Pattern Recognition. This is the website for the latest version. It's a 70-page paper, but it's well illustrated. And it's just 70 pages. There's hardly any, I think we removed all lemmas and theorems, just the basic concepts there. It takes 70 pages, but there are a lot of illustrations. There's a formal definition. Here I'm just going to give an informal, kind of just intuitive feeling for what's going on. So as a scientific view, we would like to view the reality as a multitude of interacting and involving classes of structured processes. That's all. Let's say, let's view reality as this. In fact, that's what it is. Any bottle, any desk. This actually is a process, and you will see next. If you think about a chromosome, because it has genes, this is a poor representation. The string is a poor, it doesn't correspond, because in reality it's a dynamic process. This is how it was created, and this is how it gets translated, and so on. So there is a process involved, and string doesn't capture this kind of reality. So, pardon?
But a string captures a more abstract concept, because a number, like different chromosomes could share the same DNA sequence, right?
Well,
the same chromosome in different configurations.
Yes, but you remember what I mentioned about strings earlier, that if I give you from even, never mind the sort of more pragmatic point of view, but just doing learning. If I give you finite set of strings, why there are infinitely many classes of strings currently, sort of according to the current concept that contain this finite set. That's not a palatable situation. You don't want to have that situation. Why? Again, because a string does not carry within itself sufficient information for doing this adequate recovery.
But I think there are reasonable principles to choose from among the infinitely many concepts that are consistent with a finite set. So even
this would be a lot, they would be somewhat ad hoc principles that would simply have to be put in order to deal with that big problem.
And there's a trade-off between how ad hoc or principle the solution is and how useful it is.
But the whole point, you see, of having a good formalism for classification, you don't want to introduce this kind of assumptions. You want to get into representation, and you want to move on with it and doing easily the job that you need to do. You don't want to introduce later on all kinds of ad hoc assumptions.
Depends on what you want to do, I suppose.
No, I mean, in general, I mean, that's the idea sort of representational formalism. If you look back at these first two axioms, once you represent your objects, you want your classes to emerge naturally. You don't want to do any hocus pocus, sort of. You want them to be sitting there.
But it depends, right? I mean, if somebody has an engineering objective to, build an interface to a database where scientists input their sequence and it tells them something about the likely function, let's say, of a tissue sample or something like that. A representation depends on the DNA.
I'm sorry, what are the classes here? What would be the classes?
The class might be proteins with a given function, I suppose.
Proteins with a given function, right. So that's precisely fit into this concept of class.
But a representation that depends on the DNA coding for the protein might be a more convenient and effective way to design an engineering tool.
Not necessarily. It is known that there are proteins that have very similar DNA structure or RNA structure, but they have different function, quite different function.
But the existence of those cases doesn't necessarily mean that it isn't an effective engineering tool.
No, it's an indication that you cannot grasp effectively class of this. The whole point is you want to have a reliable grasp of a class that you are dealing with. That is the purpose of classification. You said yourself, you want to be able to say that this class of proteins have very similar functions. That's the purpose, I assume. You told me that that would be the definition of that class.
Of a given type or something.
Right. So if you want this, then you automatically want, if I give you a small training sample, 5, 10, 15 proteins, you want to be able later on reliably say whether other protein belongs to that class or not. And more importantly, you won't be able to answer that question unless your class representation contains some non-trivial information related to the function of this protein in some form.
Yeah, like the DNA sequence.
No, but DNA sequence.
Yeah, you're talking about folding.
Right.
The protein, the same sequence can fold in different ways under the influence of other things in the system, which it really ties into his argument, right? The temporal process is the folding, and there are a lot of other elements involved in protein folding besides just the DNA sequence.
The chromosomes.
No, but this
So
is
the
DNA.
chromosomes are sort of the source code that describes the DNA the sequence, but the sequence has to be executed in the rest of the system that causes the folding to occur that eventually produces the behavior of the protein. You know, the behavior of the protein is really just determined by how it is folded and not just by the sequence itself.
But that fact doesn't necessarily imply that one must design induction engines that are going to reason about classes of proteins using representations of the proteins that involve all the details of the evolutionary history of the protein. And
No. We are not talking about this yet.
It's not evolutionary history. It's just an individual
the process.
Well, it's
through which
the
protein evolved.
No, we are not talking yet. I think this is what you added yourself right now. I haven't suggested that you have to plug in entire information about. I'm only telling you that your representational formalism should be reliable enough that it will capture the class in the right way with this function. And the string does not have enough information.
Depends on the class that you're trying to describe.
Well, you gave me example of a class, right? So I'm assuming we're discussing that class.
There are some classes that can be described very well by the DNA sequence.
Well, I don't know of any classes, except very trivial one, that would be described by DNA sequence.
Kinases, let's suppose. So kinases have a protein sequence, the highly conserved, that codes for a region in the protein that attaches to a particular type of molecule.
Right, but I'm not sure that I can, for example, I can give you a sequence very close to the ones that you think belong to that class that will not be doing this at all.
But for the engineering purpose of classifying real proteins that scientists really encounter.
No, when you say real, but this would be real sequence, because I can manufacture you something that will have exactly that sequence, but will not behave in that way.
But the inability of my system to handle that artificially created
It's not artificially created, this is a real thing. I'm telling you, I will create a real...
I mean that those type of circumstances will arise infrequently enough that my engineering tool will nevertheless be useful.
Why are you sure about that?
I mean, it is being, a tool of that type is being used as we speak.
No, it is being used because we don't have other tools. It is not being used because it is superior to the tools I want to discuss, because these tools have not been around yet, the ones that I want to discuss.
I guess what I'm arguing for is a possibility that abstract representations, which leave out some aspects of the items that we wish to classify, can nevertheless be useful engineering tools. That's the only proposition.
Yes, but this is general enough statement. What I want to discuss is today is what is important to have in a representational formalism that will give you a reliable way to deal with classification. Not that is what is possible to do. Of course, if you are poor in the representational means, yes, but why not to, if you have a more powerful representational means, why not to go for this? Because you will have a much more precise picture of everything.
But sometimes abstraction can be powerful because it can save you unnecessary effort in sorting through the vast complexity.
But you will see as we go down, you will see why it is true. There is a certain hypothesis you will see coming up. I'm just beginning to discuss this temporal process that is very important. First, I just want to remind you there were a few Nobel Prizes even awarded in the last 15 years in evolutionary developmental biology. If you look at the body plan, It turns out that all animals have roughly, what, 500 million years ago, there is a regulatory genes that organize during the development the body plan. And you go from mammals and you go to flies, and they're very similar. Of course, there were some modifications. So I'll come back to this. I just want you to keep in mind this. So there are regulatory proteins that organize things. So what is a body plan? You can think about each segment as a class, and this class is being modified evolutionary. But think of each body segment also as a class, and you build larger classes out of the smaller body segments. But we will come back to this one. Well, what about other data? Okay, let's look at web pages. Web pages should not be treated as static. So what we are talking about is not whether you can represent. You can always represent something in a very poor way. We want to understand what means a reliable representation for the purposes of classification. What is a good representation for the purposes of classification? That's what we are discussing. We are not discussing whether, well, you can always go into poor representations for various reasons. But to do classification, that's what we are discussing, which kind of representation. So, you know, the web page, we are interacting with the web page. So it's not a static object. If you think about it, even the way we represent web page, we are sort of interacting, and here is the time element. So there is a process involved. So I'm preparing you towards object as processes view. This is what will be done. So if you're talking about classes of objects, we are talking about now about classes of processes. So each object kind of will be a you will see now, I haven't defined this formally yet, just something like that. So what is the basic sort of formal units here? They're called primitives, more fully primitive transformations. So think of this circle. Now, this is an abstract primitive. What it defines is this. Each of these figures on the top correspond to a class of processes that are coming in. Then they interact, and something other classes are being produced, sometimes similar. So this is the unit of representation. This is sort of atomic units of representation. And what do they capture? They capture a set of events, because everything now processes, so we use events to represent things. Events understood as interaction of classes. So this is a concrete primitive. Unfortunately, the figures are the same, but now you're talking about concrete process that belongs to the class. So you can think of concrete object. So those C1, 1, and CJ2, and so on, these are the concrete processes, in other words, concrete elements of the class. So this is a concrete primitive. And this is a label. If you see there, what is the label? Label is a way, because we are not going to be writing those processes on the top, so this label B captures this sequence of processes. And well, when you observe it, you know, sequence of events, it just happened that this process turned into the terminal process, so-called, for one primitive, became an initial process for another primitive. Now, primitives are events, okay? They're just encapsulating events and that you observe during the interaction, whatever. So just some very light examples. Okay, car collision, okay? You have an event, right? Two processes come in and two processes come out. Two cars were driving. This is the two processes, two objects. And this, you know, sentence. Take a sentence. John fell in love with Susan, okay? Well, if I tell you that John fell in love with Susan, as far as you're concerned, your representation is just an event to you. The two processes, one of the way of modeling it, okay? Two initials and two terminals. Because you change your perception of those two people, so something happened to them. It's not the same John, and it's not the same Susan. It's not, something was added. This event added something to this, but you continue. John is still John, but it's a different, slightly different. This is what is shown. So Alice and Bob had a baby. Again, having a baby, two initials, three terminals. Because you knew Alice and Bob, now there are three of them. And so you have three processes. Let's go more scientific example, so to speak, is into physics. This was inspired by Feynman diagrams, but they're less precise kind of, they're capturing this situation less, but you will see now, you'll see several examples related to this. So you have primal processes. These are the processes that come in and come out. They're called primal processes. You see, you don't know, at the basic level, you don't know yet the structure of the process. So the structure is suppressed, and you just see lines. That's all what you see. Later on, you will see that this structure will become available for transform, sort of, once we learn something. So this is the primal processes, and this is the events. These are the basic events. Now let's take a look at hydrogen atom. Well, I guess no, before this we still have to take a look at sort of that view. This is just an encapsulation how to think, how to translate everything into this formalism in ETS. So here you observe state 1, you observe something A, B, C. Then state 2, you observe D and C, and what you saw that A and B merge to form D. Here is an event. So normally, conventionally, you would represent them a sequence of the states. Here, what you're representing is this. That's a representation of the situation where time is going this way. So time becomes a very important factor. Time and structural representation now become interlinked. You cannot, first of all, you cannot go back. Once you're here, that's it. Time is going down. You cannot back. So everything going one way. It's irreversible processes. So, by the way, this is what we will call formative history. I'm going to be using often this term, and gradually, hopefully, we will get to the meaning of that. So, biology gives a very good example of science to suggest how to think about objects for our purposes, for purposes of classes and classification. So what is a struct in this model? Well, here is a struct, sequence of events. Some of the events, of course, you didn't see. They were not temporally arranged, so that's okay. They're not temporally ordered. This is still representation of the process, of a small segment of a process. By the way, this has nothing to do with graphs now because of the temporal thing. It was inspired, of course, by natural numbers because according to Peano axioms, this is how the numbers are built. You have a successor sort of operation, and numbers are built that way. Now, with numbers, you can collapse them. You don't need this initially primitive tribes stored actually this sort of knots. But then we started to write 3, so the temporal part sort of disappeared. But if you look at this, you can see now you cannot collapse it because each one has a structure. Each event now has a structure, and you keep it as a part of the representation. So this is the fundamental distinction, because you cannot collapse it because each event is possibly structurally different from the other, and you have a temporal sequence. So, but it was inspired by numbers, of course, this representation. Well, here is a hydrogen atom. You have one proton and one electron, and you can see the sequence of events that correspond. This is sort of, you can think of it as a hydrogen process. They're going on this interaction. So that's a representation would be of hydrogen process. By the way, this is a structural representation. In contrast to Feynman diagrams, these were just drawings. This is interpreted as a formal structural representation because these events are formal entities. This is a lithium process, slightly more complex. And you can see even periodicity because, of course, yes, I have to move up faster. So struct relabeling, there is a formal concept of struct relabeling. So when you relabel the structs, it's just a mapping. So each struct, each class has a set of labels associated with it. So you can take all the labels of one class and map. So you allowed relabeling that preserve class belonging. But what will happen, it will reveal, you see, here are the two structs. One is obtained simply by relabeling the other one. But now you can see that they share something which you couldn't see before. You see here. So relabeling plays an important role, even though it's a simple operation.
So what are you classifying? Is it entire?
But that's right, that's an object now. Everything becomes an object. That's a representation of an object.
How do you separate out objects? Because one could
No,
conceive of
this
it
is a
one-
representation would be of a single object.
But one could
It's a
imagine
process.
one giant object that, the universe or something is one humongous process.
No, you
What's
don't want to. There's nothing to classify about. If you take the whole universe, there's nothing to classify
Yeah, so how
there.
do you
You're talking
separate
about
out
now
objects?
object, conventional web page, whatever you want to deal with classes. That would be represented like this.
But how do you decide what's part of one object and not?
No, you are modeling that object as this process. So you choose your primitives, you choose it, and then you encode it in this format.
So the same real-life objects could be modeled differently?
They could be modeled differently, but the whole point here is, as example from physics suggests, that you want to choose events that would be most appropriate for modeling a large chunk of the domain you want to deal with. It is true, initially it would not be easy to do, so you would choose certain events, but eventually you would settle, if you want to model certain class of web pages reasonably wide, you will fix the set of events which you will find and you will use that set of events. It's interaction events in terms of the user.
All right. For example, you have like chemistry. In chemistry, you deal with like molecules, right? And molecules consist of atoms. How do you decide in particular situation? Do you want to view this as collection of molecules or collection of atoms?
You will see in this formalism, it allows the stages of representation. So you will see, in fact, in this talk, how when the lithium and hydrogen will interact and form lithium hydride, you will see how it can become a primitive. This is a natural, no special tricks and essays. It's just a part of the representation of formalism now. So structurally identical structs, you notice that the labels are different here, but their structure is the same. So you can think of it when you strip them of labels. This is sort of the real object. This is abstract struct, you can call it. Well, there is a struct assembly because here they're depicted separately, but if you will notice that they share some of the primitives. So when you put them together, this is called struct assembly. What it means is that you observe them separately, but of course some primitive, for example, this primitive, is shared both by this struct and by that struct. So when you just picture them together, that's called struct assembly. So in other words, when I'm observing a face or a web page, I may have noticed only part of it, and I represent it as a part. But later on, I looked at another part of the web page, and then I will picture it. But then eventually, I have to put things together because I'm looking at different parts.
I think someone will come to get the room in a few minutes. Yeah.
Oh.
And so you probably want to move on to the main point.
All right, here is the bubble sort example. Sorry, here is an example of modeling how to model bubble sort here. Here you model simultaneously. You can do both model architecture. Architecture is static for the array, and you have a data flow. So there are primitives. This is just a simple example because it's an array, very simple. But it could be a little bit. It could illustrate some points. Sorry. So here is the model. Here is one comparison, how it would be modeled, a single comparison. Now we will see this is a single internal loop. So what you do, you bubble up to its location. This is how representation look. Look, the architecture doesn't change. This is just says this marks the boundary of cell, these events. But you can have a dynamic architecture. It would be more complex than picture. So just a bit slow. So here is sorting of this 4231. This is the, so you see here is the struct corresponding to actual process. So a 3 someone may come in?
Yeah, I believe this room is being used.
Or,
I also have another talk at 3 I have to go to. So
okay.
I think you really should wrap up.
We've got
All
about
right.
4 more minutes before I have to start.
Okay. So here is example of 2 structs. Now, here is the class description. Class description, you need constraints. Class is defined via constraints. And here is how you generate elements of the class. You allow environment to make a move, so to speak. Environment is whatever the process is that participate. But the white ones represent the elements that the events that you care about that becomes class element. So here is the picture. Here is your class element. So class representation consists of a struct plus this generating system that actually build class elements. And it's specified via those constraints. So here is the same example with web pages, just here is the simulation. This is constraints for bubble sort, and you will see now simulation of what happens, how you generate. Because this is a class description. So this is sort of description. This is how that struct is being generated. And of course, this class description could be used for construction of any struct that belongs to so-called bubble sort. Now, it turns out that there are levels. You see, if you take a struct, and if you learn some classes, the whole thing could be partitioned then, and you have a more information. So you can call it a level 1 struct because it contains this partitioning based on the classes that you have learned. So there is a formal description how to build next level classes because there are constraints now associated how they interact class elements. So still the same kind of language, and here is the class element construction. Now you use larger chunks because now you're not using single primitives, you're using class elements to build this level 1 class. All right, the same sort of a picture, but you're building out of larger chunks. So this is just some example how you can build. So here you see this is a level 1 class, but it's built out of, here is a description of classes of previous level. So you can, this is one element of a level 1 class. And just very similar idea to what you have here. Now here is the transformations. Here is the process, something happens here. Now at this level you can see the processes. Before the processes were not visible. So here is, this is how you go to the next level. It is compressed. Now here is an example with this lithium hydride. Here, this is what you have seen, but you can shrink it and it becomes primitive and you can use it for description of other. So that's sort of the last slide. This is the sort of encapsulation of what picture. You have various level classes here. Then you move to the next stage. This is when this transformation appears, when you see these interactions of larger chunks, and so on. This is how this representation. So the basic idea is this, that I don't think we can do classification without adequate representational formalism, in spite of the fact that there are so many people engaged in classification. I think that it has to do with the right representational formalism that will have an important impact, a major impact on this activity.